Hi, we start section 8.3, the hypothesis tests. So we study several hypothesis tests. So 3 types and 3 different approaches. And the first test is the goodness of fit tests. So that is the if the test if our model is good enough. So the null hypothesis is our model, H0, and the alternative is the saturated model or perfect model or full model. So that is trivial model that y hat is equal to y. So if we use all the information, we can use the perfect prediction, of course. So that is the saturated model. So we see if the our model is good enough to compared to the perfect model. Of course, we have more parameters. If we have more parameters, then we have more accurate data. So that we consider the situation that a small number of parameters they explain most variation. And if that's the case, then we pass the test. So actually the H0 is not rejected. So we use 2 methods. One is the test by deviance, and the other is chi-square test. And the second test is the tests between a smaller model W and the larger model omega. And omega should include the lowercase omega. So for example, the smaller model is eta is equal to beta naught plus beta 1x, and the larger model is beta naught plus beta 1x plus maybe beta 2x squared plus beta 3 log over x or something like that. Okay, so smaller model and larger model we compare. And we use the test by deviance. And the third model is the test for coefficients. So in the GLM, we want to see if the beta sub p or beta sub j is equal to 0 or not 0. So 0 is null hypothesis and alternative H1. So H0 may be the model that the eta is equal to beta naught plus up to beta p minus 1 x p minus 1. And H1 the same, but the one more term. So obviously, this is a special case of the previous one, the smaller model and larger model. So H1 is larger model. So naturally, we can use the tests by deviance, but also we study so-called the Wald test. So that is basically the test corresponds to the t-tests for coefficients in linear regression. And all tests are approximate. So we use basically approximation theory. So roughly speaking, that we use the second order approximation on all estimates. So we cannot say that which test is more accurate than others, but usually it's believed that the tests by deviance are more accurate than the others. It's not clear, but the test by deviance uses the likelihood function. And finally, that we use the normal approximation. But the other tests basically use the normal approximation in earlier stage. So in my understanding, so the test by deviance is regarded as better than other tests. But the test results should be somewhat similar each other, especially the sample size is large. Yeah, so at first we define the deviance. So deviance of the model is defined by basically negative 2 times log likelihood of the model minus negative 2 times the log likelihood of the saturated model. So you can see that this negative 2 times, so this corresponds to here. And the next one corresponds to the first one. So I think that this should be positive sign, but the larger and smaller. So this should be a positive sign. And we can express this using the expression in the exponential family. So we can write in this way. So theta tilde is the parameter estimate corresponds to the saturated model, and the theta hat is the parameter estimate for the model, the W. Yeah, and also this divided by phi is called the scaled deviance. And to be exact, okay, so this is the general form here, but for specific case, the deviance is here. Maybe just a Gaussian. So you can see that the Gaussian distribution that is basically so this is the likelihood function for the model. So yi minus mu I hat. Mu I hat may be linear function of the beta naught to beta p. Then the negative 2 times log likelihood. So this is likelihood function. So take logarithm, then exponential disappears, then negative 2 times. So this becomes yi minus the mu I hat. So in this specific case, the second term, the deviance, I mean the negative 2 times log likelihood for the perfect model, that is yi minus yi square. So this disappears. So this disappears and this is 0. So take the difference, then we get still this quantity. And other things that we also use the likelihood function, then you can get this function for Poisson, this function for binomial, this function for gamma function, and this is the so-called the inverse Gaussian function. Yeah, so this is the definition of deviance. So we discussed deviance and the yeah, and now that we discussed how to what distribution the D follows. So how to test the D, how to test using D, and the D asymptotically. So if n is large, then the D, I mean the sample size is large. Sorry, sample size is large. Then the D follows the chi-square with this degrees of freedom n minus p. So the reject the null hypothesis if the this D is large enough. So if D is large, then the basically difference between our model and the saturated model is large. So we reject null hypothesis and to support the alternative that is the saturated model. So chi-square distribution. So we have the chi-square distribution. So this is distribution of D. Then at the upper tail part, so this is the rejection region. Okay, and so this can be used for the goodness of fit test. And for the deviance, the test for deviance to compare the smaller model and larger model, we use the difference in two deviances. So d of w minus d of, the d of omega minus d of capital omega. So deviance is larger for the smaller model. So d lowercase omega minus d uppercase omega is positive number. And this follows chi-square distribution with degrees of freedom q minus p. Q minus p is the difference in the number of parameters between the smaller and larger model. So larger model q and the smaller model p. So this is the case that the phi is known. If phi is not known, then we take the ratio of this and the phi hat. And this follows, after some adjustment, the F distribution with degrees of freedom q minus p and n minus q. So n minus q is basically because this phi hat is estimated with the larger model. So think about the normal case that we want to estimate sigma square, then that we use a larger model that has basically the less risk to miss any factors, then we can estimate sigma square. So the larger model has degrees of freedom n minus q, so that's why we use n minus q here. So phi hat is the variance parameter, so the residual sum of squares for the larger model divided by n minus q. So in this way, then we can test the smaller model against larger model with deviance. So the larger value rejects smaller model. So next one is the chi-square tests for goodness of fit. So basically, this is the sum of yi minus mu square. So that is pretty intuitive quantity. But the variability of y, the changes, so the variance of the mu hat is here. So maybe that we should say the mu hat here. And this follows approximately chi-square distribution with degrees of freedom n minus p. So the p is the number of parameters. If beta naught to beta p, then we have actually the p plus 1 is the number of parameters. And reject h naught again if the chi-square is large. So that is pretty reasonable because the yi is our observation and the mu I hat is estimate. If the difference is small, it's good. So sum of squares is small, then the model is good. So we don't reject the model. We don't reject null hypothesis. So in this way, the chi-square test can be done. So this is the same test as the chi-square test introduced in the more introductory statistics course such as 2210. But it's of course more generalized here. And lastly, the Wald tests for test for significance of coefficient. So basically, the beta j hat is beta j is equal to 0 against beta j is not equal to 0. And that is basically estimate over standard error. In the engineering term, the signal to noise ratio. So this follows the approximately normal 0,1. So for normal case, the linear regression, this was t distribution. That was more accurate for that specific case. But here, that theory does not work. So just we have more rough approximation. So this approximately follows normal 0,1. So we reject null hypothesis of beta j is equal to 0 if the absolute value is large. Yeah, so these are the theory for the tests in this section.